Video, we are going to look at some arithmetic functions. So we are going to specifically look at the floor function, the ceiling function, and fractional part functions. So this is a continuation of the number theory course. We are going to look at arithmetic functions with a point of view to solve some problems based on that. So let me just start by defining the floor function. Floor function is also known as the greatest integer function. Greatest integer function. And basically the symbol for this is floor function is the symbol is like this or like this. So what is this GIF function? So what this means is you want to find the greatest integer less than or equal to x. So if you give any input x to the GIF function, you will get the greatest integer less than or equal to x as the output, right? So for example, GIF of 2.1 or floor 2.1 will be 2. Similarly, floor minus 1.2 would be minus 2 because minus 2 is the greatest integer less than minus 1.2, right? And GIF of an integer would be the integer value itself because it can be equal to x, right? Now the opposite of this is the ceiling function. And the ceiling function is usually written like this. It's like this. And the ceiling function is the least integer greater than or equal to x. So it's just the reverse of the GIF function. So if you have ceiling function 2.1, that should be 3. Ceiling function minus 1.2 in this case would be minus 1. Because minus 1 is the least integer which is bigger than minus 1.2. And if you have ceiling function of 3, that will be 3 itself. Once we know about our floor and ceiling functions, we can also define the fractional part function. So fractional part function is symbolized with this curly braces, and this is equal to x minus GIF of x. So the fractional part function is always positive and its value is always between 0 and 1. So value of fractional part function will always be between 0 and 1. It will be 0 if it was an integer that was input, right? So fractional part of 3 would be 3 minus GIF of 3, which is 3 minus 3, which is 0. And if it was something else, 3.1, you will see fractional part will come out as 3 minus 3.1 minus GIF of 3.1, which is equal to 3.1 minus 3, which is equal to 0.1, right? So this is a basic definition. Now, a couple of properties that you should know about these functions are the following. So floor function of x plus n is equal to floor of x plus n if n is an integer. If n is an integer. Similarly, ceiling function of x plus n would also be equal to n plus ceiling function of x if n is an integer. And fractional part of x plus n would simply be fractional part of x if n is an integer, because the fractional part of an integer is 0, right? So that doesn't contribute to any fractional part. Now that we know the basic definitions, let's look at a few problems which employ these functions in a number theory context. Okay, so the first question that we'll see is this one. Show that floor function of 2x is equal to twice of floor function of x or twice of floor function of x plus 1. So we have to prove this statement. So in most of the cases, when you have a proof type of a question, what we should start off with is try to understand what x is. Let's say x is equal to n plus f, where n is an integer and it is basically n is the floor function of x, and f is fractional part of x, right? So basically any x you can write as floor function of x plus fractional part of x, because actually that's how you define your fractional part of x, right? So this is true, therefore we can write x as n plus f. Now 2x would be what? 2x would be 2n plus 2f, right? So now if I take GIF of 2x, GIF of 2x will be GIF of 2x, 2n plus 2f, or ceiling or floor function of 2x is equal to floor function of 2n plus 2f. When I say GIF, that is the same thing as floor function, right? So here, by using the property that we saw, 2n is an integer, so it can come out, and you are left with this, right? And now this quantity, let's think about it. This is fractional part of x, fractional part of x. So fractional part of x can be in two different ways. You can think of this. It can be less than half, or it can be greater than half, right? These are the only two possibilities. It could be equal to half also, greater than equal to half, right? If f is less than half, then 2f is less than 1, and therefore floor function of 2f in that case would be 0. If f is greater than equal to half, then 2f is greater than equal to 1. And we know that it's a fractional part, so we always f is less than 1. So therefore 2f is less than 2. So what we are getting in this second case is that 2f is greater than equal to 1 but less than 2. So therefore floor function of 2f in the second case is simply 1, right? So in that case, the other alternative is you'll get 2n plus 1, right? And n was what? N was the GIF or floor function of x. So basically it's a pretty easy question. You are just taking two different cases. Fractional part of x could be above half or it could be below half. And in those two cases, you'll get these two results, right? Let's go on to a slightly more complicated question. This is find all natural numbers n such that 1 plus floor function of root of 2n divides 2n. 1 plus floor function of root of 2n should divide 2n, right? So in this problem, let's start off by assuming let k is equal to floor function of root of 2n, right? Which implies that k should be less than equal to root of 2n and obviously should be less than k plus 1, right? Root of 2n basically has to lie between k and k plus 1, right? Because the GIF of root of 2n is k. I hope you are understanding what I'm saying. So if the GIF of root of 2n is k, then root of 2n could be equal to k or it could be above k but less than the next integer, right? It cannot be k plus 1. Root of 2n could not be equal to k plus 1 because if that was true, then the GIF should have been k plus 1, right? Correct. So k here is an integer which is equal to fraction GIF of root of 2n, and we have this inequality here, right? Therefore, from here, if you square it, you'll get k square. Excuse me. You will get k square is less than equal to 2n is less than k plus 1 square. This side, there is no strict inequality. It's a strict inequality this side, right? Great. So we have getting this inequality. The 2n lies between k square and k plus 1 square. And if you think of k plus 1 square, that is k square plus 2k plus 1, right? So if 2n lies between them, these two numbers, then we can say let 2n be equal to k square plus x because it could be bigger than x. So x lies between 0 is less than equal to x, less than equal to 2k, right? Why are we saying x lies between 0 to 2k? Because k square plus 0 is the lower limit, and then k square plus 2k is the upper limit of x, right? Because the next integer after k square plus 2k is k square plus 2k plus 1, and k plus 1 whole square, 2n is less than k plus 1 whole square. So x cannot be equal to this one, right? So it must be from here to here. Therefore, this is basically 2n. So therefore, we can say x lies between 0 and 2k. I hope you're understanding what I'm saying here. Because we have said that 2n was k square plus x. X has to go from 0 to 2k, right? It cannot be equal to 2k plus 1. Right. So we have basically figured out these conditions. We have this condition here, and we have 2n lies in this range. Now, what we will say is we will use the property that was mentioned in the question. We have 1 plus GIF of root 2n divides 2n, right? So that means we can call k as root 2n. So we can say k is the GIF of root 2n. So 1 plus k divides 2n, and 2n can be written as k square plus x, right? Which means we can also say that 1 plus k divides k square plus x minus 1 plus k into k minus 1, right? If 1 plus k divides this, then 1 plus k will definitely divide this because it has a factor of 1 plus k here, right? 1 plus k will divide both of these terms. So we get this relation. Why are we doing this? Because now we can cancel k square. We can say it is k square plus x minus k square plus 1. So that is equal to x plus 1. So what we end up getting is 1 plus k divides 1 plus x, right? Great. So now 1 plus x we know belongs to what set? 1 plus x belongs to the set of 1 to 2k plus 1, right? So 1 plus x belongs to this set, and we know 1 plus k divides this. 1 plus k divides 1 plus x. So which numbers in this set will be such that they are divisible by k plus 1? The only number in this set 1, 2, 3, k plus 1 till 2k plus 1. The only number in this set divisible by k plus 1 is k plus 1 itself, right? Because k plus 1 times 1 is k plus 1. K plus 1 times 2 will be 2k plus 2, which is actually bigger and is not part of this set. So therefore, it follows that 1 plus k divides 1 plus x when x is equal to k, right? So the only way this condition is true is when x is equal to k, right? And if x is equal to k, here in this equation we get 2n is equal to basically k square plus k, and n is equal to k square plus k by 2. And basically we are getting any number n of the form k into k plus 1 by 2, which is basically your k square plus k by 2, will satisfy the condition, will satisfy the condition that 1 plus root over 2n GIF divides 2n, right? Because 2n was k square plus k, and GIF of root of k square plus k here was equal to k, and we got 1 plus k divides 1 plus x, right? So basically we have gotten our condition on n from the previous screen. That is what we did. We got the condition that n must be equal to this for the situation to happen, right? So for any k which satisfies, well, for any n which satisfies n is equal to k times k plus 1 by 2, we will be able to say that this condition is true. So it's all triangular numbers basically, right? If you have not understood what we have done here, please go back to the previous screen and go through it step by step. You should be able to understand. Fine. The next problem that we'll look at is this one. Evaluate the sum fraction GIF of 2 power 0 by 3 plus GIF of 2 power 1 by 3 plus GIF of 2 power 2 by 3 and so on till GIF of 2 power 1000 by 3. Okay. Now, this I'm doing this particular problem because we'll understand a new concept here, which is basically floor functions of rational numbers. Floor functions of rational numbers. So let P and Q belong to integer z, where Q is not equal to 0, and let R be the remainder. R be the remainder when P is divided by Q. Let R be the remainder when P is divided by Q. So we are saying let P be equal to K times Q plus R, right? In that case, we can show that GIF of P by Q is equal to GIF of K times Q plus R divided by Q, which is equal to GIF of K plus R by Q, which is equal to K plus GIF of R by Q. And now notice that because we are using division algorithm here, R is clearly less than Q, right? That is the basic definition of a remainder. Remainder has to be less than the quotient. So R is less than Q. So GIF of R by Q will be equal to 0. So this is simply K. And what is K? K is equal to P minus R by Q, right? Correct? So we have shown that the GIF of P by Q is equal to P minus R by Q, right? So that is the property that we'll be using to solve this particular problem. So what you can say, you can remember this property, P over Q is equal to P minus R by Q, where R is the remainder when P is divided by Q. So let's try to apply this property in this particular question. So we have, let's say, 2 power 0 by 3, right? So 2 power 0, 2 by 3, this will be simply 0 because here this is lower than this number, right? Correct? You can also apply this formula here. We can say it is 2 power 0 minus what is the remainder when 2 power 0 is divided by 3? It is 2 by 3, right? So that becomes basically 0, right? What is 2 power 1 by 3? 2 power 1, actually 2 power 0 by 3, I am making a mistake here. 2 power 0 is actually 1. So this is applying the formula, it is simply 2 power 0 minus 1 by 3. This is using the formula, and this is by common sense since it is 1 by 3. GIF has to be 0. So in the second case, again GIF will be 0, and using the formula, what are we getting? 2 power 1 minus what is the remainder when 2 power 1 is divided by 3? It's 2. So you're getting this, right? As you go to higher powers, you will start getting a pattern. So 2 power 2 by 3, I will say it is 2 power 2 minus what is the remainder when 2 power 2 is divided by 3? It's 1 by 3, right? Then the next higher power, 2 power 3 by 3, you will get 2 power 3. What is the remainder when 8 is divided by 3? It is 2 by 3. So as you can see here, every time the remainder is 1 or 2, 1 or 2, right? So we can conclude that whenever we know that 2 power I is equal to basically 1 mod 3 or 2 mod 3 congruent to 1 mod 3 or 2 mod 3. This happens if I is even, and this happens if I is odd. So that means the remainder is 1 here and remainder is 2 here. And remainder is 1 when I is even, remainder is 2 when I is odd, right? So if you have a summation of 2 power I by 3 GIF and I goes from 0 to 1000, right? We can obviously split this apart into separate cases where this is we can say I is even, and the other case is when I is odd, right? And when I is even, I is going from 0 to 4, 6, and so on, right? So in that case, you have 2 power I by 3 here. And in this case, I goes from 1, 3, 5, and so on. This is also 2 power I by 3. Now applying the formula, it will be 2 power I minus remainder when 2 power I is divided by 3. When I is even, the remainder is 1. So 2 power I minus 1 by 3, right? And you have to sum it over all the cases where I is even. So there are actually 501 terms in this summation. Because you're going from I is equal to 0 to 1000, so you should get 501 even terms, right? And here you will get 2 power I minus 2 by 3 because the remainder when I is odd was 2. We are using our formula and this time there are 500 terms, right? So there are 500 terms here and 501 terms here, and you can easily do the summation of this. So if you collect all the 2 power I by 3 and 2 power I by 3 from here, you will get basically summation of 2 power I by 3 where I goes from 0 to 1000. And what is the subtraction? There is minus 501 times 1 by 3 minus 500 times 2 by 3, right? And now you can just do this summation and get the answer. So hopefully you have understood how to do fractional part and how to do the GIF of a situation when there is a rational number, right? So this property will be very useful in problems, so you should keep that in mind. And now we'll look at one more question, which is basically let x be real. We have to prove that GIF of x plus GIF of x plus half is equal to GIF of 2x. So this is similar to the first problem that we did. We can say let x is equal to n plus f, where n is equal to GIF of x and f is equal to fractional part of x, right? Now, if you look at the LHS, we have GIF of x plus GIF of x plus half, which is equal to n plus GIF of n plus f plus half, right? Now, this will become n plus n because n is an integer, it comes out, plus fractional part GIF of f plus half. And basically, you have two cases. There are two cases. F could be 0 to 0 is less than f is less than half, in which case this part becomes f plus half is less than 1, in which case it is 2n. And the other case is f is from half is less than f is less than 1, in which case this side becomes 2n plus 1, right? These are the two cases that we are getting here. Obviously, on the right hand side, what is the GIF of 2x? So that is equal to simply GIF of 2n plus 2f. And we saw earlier also this is 2n plus GIF of 2f. And this also will give you the same two cases, 2n plus 1 and 2n, right? So it is obvious that both sides LHS and RHS are matching, and you will get 2n in the case when fractional part of x is less than half and 2n plus 1 in the case when fractional part of x is greater than half. So this is a simple identity and a pretty simple proof. Now the point is that we can extend this identity. We can extend it to this particular identity, x plus 1 by 3 plus x plus 2 by 3 is equal to GIF of 3x. And eventually the proof of this is exactly similar to what we did for the half case. You'll just have to take the cases where f is less than 1 by 3, f is between 1 by 3 to 2 by 3, and then 2 by 3 to 1. These three cases you will have to consider them, right? And in general, there is an identity known as Hermit's identity. So this is the extension of this particular concept. So what we'll say is if x belongs to real and m belongs to natural numbers, we can show that GIF of x plus GIF of x plus 1 by m plus so on till GIF of x plus m minus 1 by m, right? That is equal to the GIF of mx. That is the extension of what we have just now done for the case where m was 2 and m was 3, right? So this is Hermit's identity. You should know this one as well. In the future videos, I will show more questions based on the properties of these arithmetic functions. So stay tuned for more videos involving slightly harder problems. However, that's it for now, and we'll continue with the next video pretty soon. The next set of videos for the course on number theory will mostly be Olympiad problems and discussion of problem solving. So the theory part is more or less done, and you should look forward to a lots of Olympiad problems that we'll solve in the course going forward. So that's all for now. Please like the channel and subscribe to the channel as well. Like the video and let me know what else you want to know or what else you want to learn from these videos. I'll see you next time.